In this video, we're going to explain the simplex method for solving linear programs. You should already have some understanding of what a linear program is, but we'll explain it briefly here. Imagine a factory that makes 3 ornaments: canoes, dogs, and puzzles. Each of these makes a different amount of profit. Each item has to go through 3 stages: fabrication, QA, and packaging, each of which takes a different number of minutes for each item. There is a limited amount of minutes available for each stage, so we want to work out what quantities of each item to produce in order to maximize our overall profit. In order to use the simplex method, we must put our problem into standard form. There are 3 key requirements. There must be a linear objective function that we're trying to maximize. Formally, that looks like this. And here's an example of a valid objective. The second requirement is to express any constraints on the values of x1, x2, etc. as a linear function that's less than or equal to a constant. That looks like this. For example, 2x1 plus x2 must be less than or equal to 5. The final requirement is that all the x's must be at least 0. Now, let's convert the problem to a standard form linear program. We're trying to maximize profit, so that becomes our objective function. We'll call the number of canoes made x1, dogs x2, and puzzles x3. That means we're trying to maximize 11x1 plus 16x2 plus 15x3. Note that a standard form problem must be a maximization problem. Now, the constraints. In standard form, x1, x2 and x3 must be greater than or equal to 0. We can't manufacture less than 0 items, so that makes sense here. Finally, we have our other constraints. Here, the maximum time available for each manufacturing step. These must be in the form of a linear function less than or equal to a constant, which sounds more complicated than it is. They just look like this. Let's take a closer look at the constraints. To solve the linear program, we need to convert them from inequalities to equalities. We can do this by adding what are known as slack variables, S1, S2 and S3. Note that S1, S2 and S3 must be at least 0. We can then rearrange the inequalities so that the slack variables are on the left by themselves. In this form, we call the variables on the left, at the moment S1, S2 and S3, basic variables, and the variables on the right, at the moment x1, x2 and x3, non-basic variables. Remember that we're trying to maximize this objective function. For our first attempt, let's try a trivial solution. We can set all the x's to 0 and set the s's to make up what's left, the slack, if you will. If we substitute these x's into the objective function, we get 0. This clearly isn't the maximum we can get, so let's try to increase the value of one of the non-basic variables. Here, we'll increase the value of x1. What's the maximum value we can set x1 to? In the first equation, it's 12,000. Otherwise, one of the other variables would have to be negative, which isn't allowed. In the next constraint, x1 can be at most 6,900. In the last constraint, x1 can be at most 4,800. This last constraint is the tightest, so we're going to rearrange it to make x1 a basic variable. First, we'll swap the half x1 with s3. Then we can double the whole equation. Notice that x1, which is now on the left, has become a basic variable, while s3 has become a non-basic variable. We can then swap this in for our old constraint and start substituting the right-hand side for all the other non-basic x1s. In the first constraint, then in the second constraint, and finally in the objective function. Now the basic variables are s1, s2 and x1. The operation that we've just performed is called a pivot. the non-basic variable x1 is known as the entering variable, and the basic variable s3 is known as the leaving variable. Let's perform another pivot. This time, we'll choose x2 as our entering variable. In the first constraint, it's at most 5,400. In the second, 6,300, and in the last, it's at most 7,200. The first constraint is the tightest, so we'll pivot again, this time with S1 as the leaving variable. First, we swap the entering and leaving variables. Then, we multiply the equation by 3/4 to normalise it. Next, we can substitute for x2 in the second constraint, then simplify that, and substitute for x2 in the third constraint, and again simplify. Finally, we substitute for x2 in the objective function and simplify. Now we can do the final pivot. This time we'll choose x3 as our entering variable. In the first constraint, x3 can be at most 14,400. In the second constraint, it can be at most 800. And in the last constraint, x3 can be at most 1600. The tightest bound comes from the second constraint, so we'll use s2 as our leaving variable. Once again, we'll swap the x3 term for the s2, then multiply by 4 to normalise the equation, and swap that in. Let's do another set of substitutions, this time substituting x3. We can substitute into the first constraint and then simplify. We substitute into the third constraint and then simplify. And finally, we substitute into the objective function and then simplify. Now, look at the objective function. All of the remaining variables have negative coefficients. S1, S2 and S3 cannot be less than 0, and if we try to increase any of them, the value of the objective function would go down. That means we've finished the simplex method and we've found the maximum answer. Let's set S1, S2 and S3 to 0 so that we can see it. We can now see that the maximum value of the objective function is 102,000. That's our profit. In order to reach that maximum, we have to set x2, the number of dog ornaments, to be 5,100, x3, the number of puzzle ornaments, to be 800, and x1, the number of canoe ornaments, to be 600. So, to recap, here are the stages of the simplex method. First, put the linear program into standard and slack form. Then, choose one of the non-basic variables that still has a positive coefficient in the objective function. Find the tightest constraint on that variable, then pivot, rearranging the constraint and substituting it into the other constraints and the objective function. Repeat this process until you have found a solution. Note that the time complexity of the simplex method is exponential. There is no known way to pick the correct pivots in order to solve the problem quickly. However, in many practical applications, the simplex method turns out to be fast. It will often converge on a solution in approximately the order of the number of constraints. That's all there is to it. Thanks for watching.